就是上一个。你是要一个密码？哦。啊，他们要找什么
36773他的教室专有3673应该就有，但是第一个通常是会很热情的欢迎，然后才会推荐到。然后他的麦克风是在摄影机上，所以最好是要带麦。
好，我们要等一下帮他用，就带着嘛。
对啊，然后这里有个 mute 啊
mute，
如果按到的话就没声音。好用。
样就开了。
开了，啊你就
Hello。哦有。好，放口袋。太远，太近，它很强，是不是？
你不觉得声音还蛮大的吗？
真的。Sorry。Hello。
这边应该有开。
好。
这个有马上插进去就可以用。
等一下，
对，
这个我
这个插
手机。
这边就可以了。
好吧。发生什么事？
哦，应该不用理它这个，因为我现在插了一个 USB，插了那个风衣盒的 USB，应该可以不用理会它。
OK。它变延伸，所以我要做什么事？
你就把这个关掉就可以了。
把这个关掉。
然后把你刚刚原本那个风衣盒
OK。
就放一样的话，一样的画面。
OK。好，看起来是 OK。好，感谢。
下一页啊，这个是
雷着。OK， 好，谢谢。太好了，顺便来插我的。因为我忘了带我那个充电器，我怕我手机没电。
如果你要喝水的话，一瓶这边有。
OK， 好，谢谢。OK。
其实课是10分开始。
OK， 没关系，
叫他们先来。
没关系，大家慢慢来。
我们再等一下下哦。
不好意思，我可以现在去厕所。可以，好，再去
厕所的话要，以前你跟老师讲说厕所怎么走。对。
不好意思。
哦，应该可以。
Test。
哦，你怕它键没有声音？对。没有。好像没有声音。没有声音吗？哦，他说是接 HDMI。哇哦，什么意思？他好像是接 BGA。没有声音，但是有影像，对，有影像。不然就是跟他讲大声。有影像，然后声音就是没有。对，随便做，随便做。喂。
喂。喂。
没有声音了。有，OK。好，谢谢。
所以现在那边有人吗？现在那边没有人。好，所以根本没有人嘛，哦。好，我们开始今天的演讲。今天因为学校把我们的教室抢走了，所以我们现在必须要分开我们的演讲，有摇滚区跟看台区。现在看台区好像没有人。今天好好点名，这铁定没有120个人。好，我们今天很荣幸邀请到清大物理系的老师黄一平助理教授。黄教授是2008年在清大物理拿到学士之后呢，他就到UC Boulder 在科罗拉多州美国，2017年拿到博士。之后他到了 Max Planck Institute 在 Dresden 复杂系统的物理所担任博士后研究员。那也在Porsche Institute 这是在瑞士做了1年之后，今年2月回到清大物理担任助理教授。这边如果满了，就要到隔壁去。这边都满。好，那黄教授的专业领域是凝聚态物理理论。今天他要带给我们的演讲题目是 Emergent Quantum Phenomena in Constraint System。让我们欢迎黄教授。
我突然想到一件事，我应该讲英文还是讲中文？我应该都可以。
都可以。
OK。
你的投影片都是英文吗？
目前都是英文，但我另外一个版本是中文的。
没有关系，那你就讲中文。
讲中文吗？
对。
OK。
对，我可以鼓励你。
OK， 鼓励讲中文，那我换个投影片。
因为我们有不会讲中文。
有外籍生吗 ？OK。OK， 好。OK。That's fine. Okay, so I need to say that because I don't have the Chinese version of the slides yet, so maybe I'll just talk in English. So today I'm going to talk about emergent quantum phenomena in constraint systems. Here's the outline of today's talk. So basically, I'll start from a brief introduction about phases of matter. And basically, it's about the quantum phase of matter, and I'll try to explain what do we mean by quantum 1.0 and quantum 2.0. Okay, and basically, the primary difference is about the entanglement in quantum many-body systems, and I'll try to motivate the talk by describing why entanglement plays a fundamental role in the basic science research and applications, and try to motivate you with some reasoning why it is important and why it is interesting. Within a quantum phase of matter actually is a really broad research topic, and today I'm going to focus on something that's called quantum spin liquids, and basically it is a many-body spin system which are highly correlated, and they have some interesting property about the entanglement structure. And I'll try to use this example to elaborate the idea that why when we try to realize a highly entangled wave function, that the constraint actually plays a very important role. So for that, I'll try to describe two related subject. One is about the frustrated system. That is where we will discuss some basic idea about the quantum spin liquids. And the second part is something that we are doing recently, is about the correlated many-body dynamics. Okay, so basically that's the purpose of today's talk and outline. And before I do anything, I'll just thank my collaborators. First is my PhD advisor, Mike Hermley from Boulder, and Gang Chen, who is now a professor at Hong Kong University and Fudan, and also a collaborator from Taiwan, Professor Yinzhe Gao from NTU, and his student, Kaixin Wu, now who is at the Boston University. And I will spend some time to talk about this work, which is published around 2014. It's basically an idea of dipolar to polar doublets. So what we found is that in the material, basically, most of the time, if the symmetry is low enough and if it is magnetic, basically we have a two-level system. And usually when we have two-level system, we try to model our system as some kind of pseudo-spin operator. And those pseudo-spin operator usually carries a magnetic dipole moment. That's how we start to understand what is a magnetic material. However, what we found is that when the system has strong spin-orbit coupling, actually those pseudo-spins could transform in a very interesting way, such that this kind of local degrees of freedom actually act like a mixture of dipole moments and octupolar tensor. So that's basically what this work is about. And the second work, I don't have time to discuss in real detail, but I think Professor Injo Gao has given a talk previously. So basically the idea is that what we found is that when you have a strong spin-orbit coupling, the quantum effect of your system is pretty much anisotropic, and this anisotropic interaction could lead to some very novel behavior. So that's the two work related to the equilibrium phases of matter related to quantum spin liquids. And the other part of the talk, or the other subject, is the correlated many-body dynamics. It's basically collaborated with the Dresden group in Germany. And the first part is about the identification of a special phenomena, what it is known as the dynamical quantum phase transition. And the second part of that, of this research is a very interesting result that we just got recently. It's about how the gauge constraint, that is basically, we are studying a lattice gauge theory system, and we found that this gauge symmetry or the gauge constraint actually plays a very interesting role, such that even though the system has no disorder, that's basically it is translationally invariant, but we still have some very interesting slow dynamics, which we call it disorder-free localization. Okay, so that's like the basic plan for today's talk. And also, since even though it is a plan, there's no pressure that we need to go through every every subject. So I'll try to say things in a more, friendly way to some extent, like wave my hands and give you some flavor about what's going on. So if you feel like you want to ask some question, you can just raise your hands or interrupt me, okay? So let's start with the introduction, like why it is interesting from a fundamental physics perspective that study of this kind of highly entangled quantum phase of matter is a fruitful direction, okay? So for condensed matter physics, I would say that one of the most important goal for us is to understand how matter, like different forms of matter, are classified or are formed. So here we just show several different important classes, like for example, the important discovery of transistor. Basically, it's about the semiconductor physics, and also some very interesting phenomena like fractional quantum Hall effect, and topological insulator or liquid crystal and superconductors. So there are tons of different phases of matter for us to understand. So how to have a unified framework to understand all of them. So one of the very successful framework is basically proposed by Landau. So what Landau proposed is that actually in order to understand different phases, we can use an object which is called order parameter. And starting from the understanding of the order parameter, we can try to construct something called Ginzburg-Landau theory. And from there, we can try to define different phases of matter according to the symmetry property of your order parameter. And also, we can use it to study the phase transition between different phases of matter. So it is very important in the sense that it is a phenomenological theory that it can be applied to very different kind of phases of matter, ranging from superconductor, which is a quantum system, to liquid crystal, which is a completely classical object. Okay, so so that's good. It is super powerful, but as a scientist, we always want to ask a question: how to go beyond what we understood already? Okay, so if we try to think back about what is the assumption of Landau theory, actually it's based on several assumptions. The first thing is that the order parameter that we just discussed need to be defined in a local sense. That's basically, given a local information of your material, like within some spot or something, then you need to be able to define some physical quantity to characterize what is this phase, okay? And in addition to that, you need to study the symmetry of your local order parameter, okay? So in order to go beyond Landau theories, there are several ways you can try to go beyond that. So one thing is try to break the idea that this, the order of your system actually can be defined locally. So in order to avoid that condition, there are two ways, basically what people discover right now, at least there are two ways. So one is to include the quantum mechanics. And in quantum mechanics, one of the very important ideas that go beyond the local structure is the idea of entanglement, okay? So that's why entanglement is a very important, plays a key role if you try to understand the phases of matter to a deeper level. And the second part is that maybe there are some order that cannot be characterized by information that is really local. So what does that mean? If you have something that relates to the topology of your wave function, that means that you need to understand the structure of your wave function in a global sense in order to define this topological quantity. So that's basically the two ideas to go beyond the conventional Landau theory. So another way to go beyond Landau theory is actually you can go to another extreme. That's basically what we are discussing right now are all phases of matter in equilibrium. How about when the situation is out of equilibrium? When it is out of equilibrium, basically we know that when you study the statistical mechanics, you no longer have the nice Boltzmann distribution wave function for you to study it. So that means that there are more possibility and there are more interesting unknown results for you to look for. So, so today we'll try to talk about both of them. So let's start from the first part about the entanglement. So, so this is the Nobel Prize of 2016. So there are three recipients. One is the professor at Princeton, that's Professor Duncan Hoden, and the other two are contributing the important idea of Kosterlitz-Saulers transition. So this Kosterlitz-Saulers transition is basically the case where the important ingredient that drives the phase transition is actually the vortex, which is a non-local object. That's basically a topological defect. So in that sense, this phase transition is not captured by Landau theory. And, but that's not the primary target for today's talk. So instead, I'm going to talk about the new idea that is brought by quantum entanglement. So if you go to the Nobel Prize website and try to look for this figure, it's basically a diagram or like that shows the importance of Professor Duncan Hoden's discovery. That's basically this Hoden phase. It is a special quantum phase that's defined in one dimension with spin equal to one spin chain. And from the figure, you can see that it looks like some kind of nice illustration that there are some very interesting structure like these little bonds and this oval. So basically, this little bond represents the singlets. That is the EPR pair of these two spins that can form. Okay. So you can see that this is a very regular arrangement of entanglement pairs. And this special phase is what later called as the Hoden phase, because this phase is interesting in a sense that when you have a special symmetry to protect your system, then there's no way for you to deform this wave function from this so-called Hoden phase to the product state wave function without closing the energy gap. So in that sense, this phase is protected by the symmetry. So it is later named as a class of a wave function that is called symmetry-protected trivial phases. Okay, or sometimes people call it symmetry-protected topological phases. Okay, so at this moment, I think at least people can get the idea that this is a 1D chain, and we kind of try to entangle these degrees of freedom by their neighbors. So in one dimension, it is a very straightforward way of generating this kind of wave function. So how about in 2 dimensions? Are there some different things, or even in higher dimension? And it turns out that the answer is yes. There are even more exotic phases. That's basically this kind of entangled pattern, basically defined in a higher dimensional lattice. So here I'm just using a special case that's basically a 2-dimensional lattice, where this red oval represents the EPR pairs for different sites. So this special wave function can be understood as the linear superposition of all different kind of coverings of these red ovals. So this kind of wave function is a prototype of the idea that is proposed by Phil Anderson back in the 1987. That's what people now understood as the quantum spin liquid wave function. Okay, so you can see that there are some complicated pattern of entanglement, and it can be sustained in a higher dimension. In this case, it's a 2-dimensional system. So, but there's a difference comparing with the Houdan phase. That's basically when you break the symmetry, in the Houdan phase case, the wave function can be adiabatically deformed into product state. But for this kind of quantum spin liquid wave function, even without the symmetry to protect it, you are not able to deform it into a product state wave function. So that makes it a very special family of quantum many-body wave function. Okay, so also there's no classical order in the sense that in order to understand how these red ovals are arranged, you need to devise a very different concept. So this kind of concept is not captured by Landau's theory. Okay. So, so here I just talk about 2 different family of states. Oh, by the way, I forgot to mention another thing. This kind of quantum spin liquid is also known as the symmetry-enriched topological order, because without symmetry, it is already a special class of topological order phase. But when you include symmetry, then there are more different kind of wave function that can be classified according to their symmetry. So here I just give you a very quick summary about what are these abstract theoretical ideas and what are the corresponding examples. So for the symmetry-protected topological phases, we just introduced the Houdan phase, but actually there's another important family of phases, this topological insulator, that basically is categorized in these SPT phases. And the symmetry-enriched topological order, including like spin liquid that I just discussed. And in this research area, people ask the question as, for example, like how symmetry acts on this spin liquid wave function and all this kind of interesting interplay between the topological structure and the symmetry property of this wave function. And that is basically the theme for the study of symmetry-enriched topological order in the past 5 to 10 years. Okay, and here are some very interesting reviews, and I'll just skip that. Okay, so I hope that this very short introduction kind of give you the flavor that why this is a fundamental interesting subject to explore, because this is basically trying to understand the entanglement structure for the many-body wave function. Okay, so in that sense, it is fundamentally interesting. But we can still ask the question, like, why it is important for any application and why should we care, right? Maybe somebody care about it, but I don't care. So, so the idea that I think is a little bit emphasized is that when we are trying to talk about the development of quantum computer, I think one of the important lesson that we can learn is like try to look back the history about how classical computer emerged from our history. So at the very beginning, we have the idea of classical computer, and we try to build something like this gigantic machine that's formed by vacuum tube. And now you can only see this kind of vacuum tube where you are trying to have a really high class sound device. But back in that day, basically, you are facing the difficulty of maintaining this kind of giant beast, because maybe one of the vacuum tube will break down or something, then you are not able to operate your machine in a normal way. So it is until very late, that about 1947, that transistor is invented. So once transistor is invented, basically it brings the possibility that you can have a really high density of computational unit. So once you have this kind of advantage, then you are able to have the prototype of modern era computer, okay? So if we look at this very short history, then you'll see that the really key important object is the invention of transistor. So if you go back to the Nobel Prize website again and try to read the Nobel lecture about why how the transistor is invented, you'll see that Bardeen is the guy who invented this transistor. And there are some other two big shots, William Shockley and Walter Bratton. So basically what Bardeen's point of view is that the success of transistor is actually based on two very important ingredients. One is that we know the theoretical base for semiconductor physics. That's basically we know quantum mechanics for semiconductor very well. That's one thing. And the second thing is actually from the experimental side, that people are able to purify the sample to a very high quality level, such that engineer this material becomes possible. So we can ask the similar question, like around 2019, Google successfully created a 53 qubits quantum computer and use it to perform some calculation, and suggesting that the potential of this quantum computer is actually pretty huge. But we can still ask the same question: what are the theoretical foundation that we need, and what kind of experiments that we need in order to build our transistor for the quantum computer? So it turns out that I think the key question is we need to understand many-body entanglement pattern. And the reason for that is twofold. The first thing is that the important thing that quantum computer is different with the classical computer is we are able to use the special structure in the quantum mechanics. That's basically entanglement, okay? But entanglement can be just two-body entanglement or three-body entanglement. Why should we care about the many-body physics? The reason is that as we increase the unit number of your qubits, eventually you'll reach a level that you need to study the collective behavior of all these qubits. So in that sense, we need to understand the many-body entanglement pattern better, including how to stabilize them and also how to manipulate them such that they are able to do whatever we want to do. So I think that's the key question, and people are trying to do that. And nowadays, people try to describe this kind of physics that is directly related to the physical observables in the quantum mechanics, and then characterize them as quantum 1.0 research. And for the later part, that basically we try to explore what happened in the quantum many-body system, but with emphasis on the entanglement is what people consider as the quantum 2.0. So in that sense, it is important to understand the entanglement structure for many-body wave function. So it is a research area that with both fundamental interesting question and really important application in the future. Okay, so I think now I'm going to switch gear to some specific idea or specific phenomena that is related to my research. Are there any questions so far? Okay, so if not, I'll just continue. So when we talk about spin liquid, probably you will read the idea of spin liquid in different contexts. So one of the primary important idea, basically, people discover in the past 10 years is that usually when people say something is a spin liquid, what they meant is that there's a spin system, and when I try to cool down my system, what we found usually is that the system start to order in some magnetic pattern. But spin liquid is another kind of phenomena that when you try to cool down your system, actually it does not order. So in the past, people used that as the definition of the spin liquid. However, it is not a really nice definition in the sense that it is defined by what it is not, right? You know, there are tons of reasons why this thing doesn't order. Why should I use it as a definition? So what is more important in the past 10 years is that people found that there's a better way to define what is a spin liquid and basically bring the idea of entanglement from the study of quantum information into condensed matter physics. That's basically the modern definition for spin liquid is that this is a highly entangled wave function that is formed by these spins. And importantly, there are some emergent excitation which cannot be explained using the Landau theory. So I'll try to scratch the surface about what are these emergent excitation a little bit later. But I'll just want to say it is really important to know what different fields are doing. So in this example, it is a really nice example that if you study physics, and sometimes you might find that the idea from quantum information could be useful, and you take it into your area, and it can help you to sharpen your question and make some progress. And here are some very nice review articles. If you are interested in this research direction, you can try to check that. The bottom line is that this new definition actually changed the research direction for the community into the study of entanglement pattern of a many-body wave function. So in principle, it is a really complicated story, but let me just try to use some very simple idea to demonstrate what are these. So we know what Bose-Einstein condensate is. That's basically when you have a bunch of bosons and you try to trap them in the simple harmonic oscillator or something, and then you try to reduce your temperature. After a certain critical temperature, you'll find that these bosons prefer to go to the ground state, and everybody just stay in the ground state. So that's what Bose-Einstein condensate is. So it is proposed theoretically a long time ago, but the experiment is realized by these three gentlemen around 1990s, I think. So, so basically, that's how the wave function looks like. It is a product state of phi I. I means like different particles, basically different bosons. But all the bosons share the same ground state wave function. That's just this phi 0. Okay. So quantum spin liquid, in a sense, is very similar to this Bose-Einstein condensate, that the wave function is a macroscopic wave function. That's basically, even though it has the quantum mechanical nature, but it is still survived in the macroscopic world. For quantum spin liquid, the situation is a little bit different, that it is a macroscopic quantum phenomena, but instead of forming a product state, it is forming a superposition of this kind of different configuration of dimers. So in that sense, it has more entangled structure in the wave function. Comparing with the Bose-Einstein condensate, they are basically just a bunch of product states, so there's no entanglement in there. Okay. So so that's like just a very a conceptual idea. So let me try to write down a very special model, which is this torical model that can explicitly show what is the wave function that I'm talking about. The reason I write down this model is because first, it is exactly solvable, even though it looks very strange. For example, you have these 4 spin products together, and also another 4 spin product together. So this Hamiltonian contains only these 2 terms, but these 2 terms commute with each other such that this really artificial Hamiltonian can actually be solved exactly. Okay, so if you are interested to solve it, you can just Google torical model and how to solve it, and then you can find tons of ways explain how to solve it. So I'm not going to talk about the detail of how to solve it. I'm just going to show you what is the ground state wave function for this torical model. So at this moment, please trust me. I'm not just telling you some incorrect results. So the ground state wave function for this torical model actually can be understood using these patterns, okay? So let me explain what these are. So the first thing is that there are black dots. These black dots represent the spin 1/2 states with tau x equal to +1. That means that your spin just pointing in the x direction, okay? For those black dots, they are all pointing in the same direction, that's in the positive x direction. But now you can play a game. You try to draw a closed loop. And this closed loop will pass some of the spins. For those spins that is passed by this closed loop, the spins needs to be flipped. So that means like for those spins that is on this purple or blue loop, they have the tau x pointing in the negative axis direction, okay? So in that sense, you know that this one figure just represents how the spins are ordered in this component. In this case, these 4 spins that is enclosed by this blue loop has a tau x equal to -1. And in this case, you have 2 different loops that has tau x equal to -1. And the ground state for this torical model actually is formed by all superposition of different loop covering. That is basically you can have different numbers of loop, you can have different shape of the loop, you can have bigger loop, small loop, and you can have connected one, disconnected one. And you just include all of them and just sum them up together. So that's the ground state wave function for this torical model. So in principle, you can try to use this torical model and try to create the excitation. But I think due to the limit of time, I'm not going to talk about the detail of that. But basically, the idea is very simple. In the ground state, it is formed by a bunch of closed loop. So how to create the excitation is you violate this closed loop condition. You just cut the loop open, then you will have 2 open ends, for example, like this. Then those configuration with loop with open ends will form the basis to represent your excited state. And if you have all the superposition, then you've got your excited states in this Hamiltonian. So why it is important? Because now you recognize there's a very strange condition that says that the ground state needs to be formed by closed loops. So if it is just a product state, which means that you can only know what happened nearby your neighbor, then there's no way that you are able to impose the condition that the wave function has a big closed loop or open closed loop. So in that sense, this ground state wave function is really highly entangled. Okay, so why I'm talking about that? Because there are some problem about this model is that I think we already agreed that this is a really artificial model. One of the very important things is like how to find it in nature. If it is really possible that nature can provide such a wave function, is it possible to find spin liquid in our material or some artificial system? So I'm going to just show some of the experiments like this Kagome lattice Herbert Smith site that's synthesized around 2015. And they have a very special family of spin liquid that's known as the Dirac quantum spin liquid. And also recent experiments on this ruthenium trichloride, there are also some very interesting thermal transport experiments suggesting that it could be a very interesting spin liquid. Okay, so there are already various different kind of spin liquids, and one of the other one that's related to quantum spin ice. I think Professor Liezhen Zhang in the Chengkong University work on this material intensively, and I'm just going to say something about my contribution in this subfield, and hopefully it will be an interesting subject for people to explore. Okay, so I think I'll just give a very quick introduction about what is this family of spin liquid, or also known as the quantum spin ice. So the idea is quite simple, that basically the model that show this kind of quantum spin ice physics is the XXZ model defined on the Pyrical lattice. So Pyrical lattice is, can be understood as a corner-shared tetrahedral that is connected in a really regular way, like this. And on each vertex of the tetrahedral, there's a quantum spin sitting on it. And the way these two spins interact with each other is through this XXZ Hamptonian. So what is the XXZ Hamptonian? Is basically, it contains two parts. The first part is what we call the ice part, or the icy model part, that basically you have a product of SZ and SZ operator. And in order to minimize the energy of this term, what you want is actually you want to have a total spin on a single tetrahedral to sum up to be 0. Since there are 4 spins on a single tetrahedral, in order to have a total spin sum up to 0, you need to have 2 pointing inwards and 2 pointing outwards, such that you have +2 and -2, so it cancel each other. And if you have 4 vertex, you have the degrees of freedom to choose which 2 vertex to point in inwards and which 2 to point outward. So you have 4 choose 2 configurations. So here I just list the 6 configurations such that the total spin sum up to 0. Okay. So this manifold is special because if you try to follow this rule, and you try to arrange your spins on the tetrahedral, you'll find that there's a huge degeneracy because you can choose which one to point in inward and which one to point outward. And that suggests that this system is actually highly frustrated, okay? So one very interesting observation that's made by previous research is that these spins are usually not usually, these spins should be considered as some kind of magnetic field. But if you try to think in another way, that try to express this little error as some kind of direction for your electric field, then the condition that you need to have all the spins sum up equal to 0 in this single tetrahedral actually correspond to the Gauss law that we learned in the undergrads, that 2 electric field pointing inward, 2 electric field need to point outward. Then if you make this connection, then you kind of have the feeling that this model is supposed to have some connection with the electromagnetism that we have learned before, okay? So, of course, this part is just the classical part. We can ask what happened if, because we know that it is a quantum spin, we can ask what happened if we turn on the quantum fluctuation. So once you turn on the quantum fluctuation, then different spin orientation in the previous case will correspond to different electric field line configuration. And turn on quantum fluctuation means that this electric field line will start to fluctuate in your lattice. So what that means is that now you have a bunch of loops, and these loops now start to hybridize with each other through this quantum tunneling event, okay? So very similar with the previous case that we, in the 2-dimension torical model, we said that, you have a bunch of different closed loop pattern and form superposition, and you have a highly entangled state. So in this case, you also have this kind of results that when this electric field lines start to fluctuate in 3 dimensions, you actually has a quantum spin liquid that is highly entangled and cannot be deformed into a product state. And that is what that is basically the phase that corresponds to this quantum spin ice phase. So you can ask, like, okay, suppose that's all true. As an experimentalist, I will still need to ask how to probe this thing, right? Like you tell me a lot of story, like, but as an experimentalist, I would like to know how to probe it. So the idea is that when you try to form this theory, as we mentioned that in addition to the electric field line, you have dynamical fluctuations from the quantum mechanics. So you can ask electric field, if it is static, that corresponds to the static electromagnetism that we learned, that charge is not doing something that depends on time. But once you have dynamics in your system, then eventually you should consider electrodynamics instead of electrostatics. So when you consider electrodynamics, one of the very important ideas is that when electric field is fluctuating in time, it will generate magnetic field. And magnetic field will fluctuate in time, and it will generate electric field. And the intertwine between this E field and magnetic field will give us a very special phenomena that is basically the photon. So we have light, okay? So you can ask, in this system, is it possible to have this light? And it turns out that the answer is yes. If you try to study this spin system defined on this lattice and using some numerical method called quantum Monte Carlo and do this simulation, you'll find that at low energy, there's a very special dispersion relation that corresponds to this artificial light. That's basically you have E field and B field, and they will just give you something like emergent photon. So it's kind of interesting because in a sense that our system is a bunch of two-level system, right? Just a bunch of spins. And we know that light is something that came from a gauge theory. And gauge theory is something that has a special symmetry that people consider as gauge symmetry. So in this system, at the very beginning, you don't have any gauge symmetry because you have the global symmetry that is basically the U1 rotation about your system. But at the low energy, it turns out that you can have some symmetry that is local that can emerge from this spin system. So that's very cool. So in that sense, this model plays a special role in the study of quantum spin liquid because you can see how the gauge structure emerged from this kind of spin system. Okay, but of course I didn't show the detail of calculation how to do it, but just trust me, and if you are interested, I can tell you more. So the important thing is that how to realize that. So the idea that we propose is to use spin-orbit coupling in this pyrocle material. So why it is important, I'll just skip this slide, but it is also very important for another family of material. But let's try to focus on the pyrocle lattice that we just discussed, okay? So if you look at the material and you try to write down the two-level system for your magnetic ion and try to consider the lattice symmetry in your compound, basically the pyrocle space group, and you impose the time reversal symmetry to ask what kind of magnetic model can be written down. And it turns out that this is the situation if you assume that the magnetic ion can be modeled by magnetic dipole moments, okay? So if you assume that the magnetic ion carry a magnetic dipole moments, then the model is really complicated. It contains, the icing part and the XXZ part that we want, but it also contains a bunch of garbage that we don't know how to deal with, okay? So is it like the only way out? Because if it is the model that we really need to understood in order to explore the possible materials, then it will be a disaster because there's no hope for us to study it. So the idea that we came out is that something is missing in the previous study, that even though the low energy states will be formed by a two-level system, it doesn't mean that this two-level system will form a magnetic dipole moments only. It could form something that carry a special property under the symmetry. So what we found is that in order to realize this kind of special degrees of freedom, what you need to do is that you need to really consider how your local crystal field structure is deformed. So in this pyrocle material, there are three kind of possible situation. One is the ideal cubic lattice structure. That's basically, just like a dice. You have the symmetry of a qubit. But you can also extend or elongate or compress along the local 111 axis. And this different local environment will give you different kind of ground state configuration of your two-level system. And it turns out what we found is that there's a special ground state that is represented by a different representation of the doublets. And if you take these doublets as your degrees of freedom, then you will form a very simple model, which is called the XYZ model. So it is almost like our XXZ model, but with a little bit anisotropy in the XY plane. Okay. So, I probably will not have time to discuss about the detail of the symmetry argument, but you can have a quick understanding about what is this doublets. So usually when we form a doublet, we said that we can form it by spin 1/2 and minus 1/2. That's the two level, and use that to form your pseudo spin operator. But this kind of doublets actually is formed by spin plus 3/2 and minus 3/2. And this 3 is kind of important in the sense that in this pyrocle lattice, there's a 3-4 rotation. So when you perform the 3-4 rotation, use these degrees of freedom, you'll find that this pseudo spin will not transform as a usual vector. So in that sense, it contains the octupolar component for these degrees of freedom. So it is kind of cool, and the model is simple in the sense that it is possible to explore the phases of this model using quantum Monte Carlo in a huge parameter region. So you have a chance to use to combine the material knowledge and the numerical physics and the theoretical physics and explore whether it is possible to find this artificial photon. Okay. So also because we are doing the symmetry analysis, even though I draw here is the level scheme for d orbitals, it can also be applied to rare earths like f orbitals. So the model is actually quite versatile to describe the pyrocle lattice. So here are some of the materials that we proposed, and the most interesting one is the recent discovery of this serum-based pyrocle material, because in the last, last year and the year before last year, there are 3 independent groups. They identified the degrees of freedom of these dipolar octupolar doublets that we proposed. So that's really encouraging that they found these degrees of freedom. But the unfortunate fact is that in order to see this photon mode, you need to go to really low temperature and really high quality of your sample. And there's also some complication from the theory side that to interpret the corresponding neutron scattering studies. So the photon mode is not yet observed. So we don't know whether this the ground state of this object is really a quantum spin liquid or not. Okay, so it is still research ongoing. Okay, good. So so I think I just try to show you what octupolar quantum spin ice should look like in a beautiful diagram. But it isn't, of course, in real life it is never this kind of. You will never have these beautiful interpretations. Okay, so I think that's like a very quick introduction about the physics of quantum spin ice. So I think now I'm going to switch gear from the equilibrium physics in the solid state physics to another research area, which is the synthetic quantum matter. But before I go to there, are there any questions about the quantum spin ice physics? Yes? Yeah, please.
I'm wondering what is the smoking gun of the behavior of the ice or the liquid?
The smoking gun, that's a very good question. So, wait, where is it? I think Tyrone is asking, suppose we have it, what is the definition? Wait, why Why the nice dispersion is gone? I think it is here. Yes. So I think Tyrone is asking, as when we propose there are some exotic states of matter, you need to tell me what to probe, right? So if you don't tell me what to probe, I basically have no chance to identify these states of matter. So on the big umbrella of exploring quantum spin liquid, the first thing we should know is that I'm just introduced a very special type of liquid. It's called a quantum spin ice, but there are different family of quantum spin liquid. For example, you can have Dirac's quantum spin liquid, you can have topological quantum spin liquid like the Z2 toric cold, and you can have this U1 quantum spin liquid or quantum spin ice in the particle lattice, and all other things. So most of the most important thing is that these states of matter are characterized by entanglement. And from the undergrad's quantum physics, we know entanglement is not something that you can probe. Then you immediately face a question like how to probe the entanglement structure. So that's why I picked this example, the U1 spin liquid, because the fact that you have this low energy linear dispersive mode in a disordered system is a signature that you have the entangled wave function. The reason is because if you have a disordered phase, usually you don't expect to have a low energy linear dispersive mode, because it only happens when you have some spontaneous symmetry breaking. For example, if you have a lattice, you have photon mode, phonon mode. For phonon, basically at low energy, it will be linearly dispersive. In addition to that, in the magnetic system, if you have a Heisenberg model, you could also have spontaneous symmetry breaking, then you got spin wave. But this system does not have spontaneous symmetry breaking in the magnetic system. That's the first thing. And the second thing is that the model does not have the continuous symmetry, so it will not have the conventional Goldstone mode. So if that happened in a disordered system, without spontaneous symmetry breaking, and with a low, and the symmetry of the system is so low, but you still get some kind of dispersive, linear dispersion at low energy, then it is something unusual. So in that sense, if you try to shine neutron scattering to your sample, suppose you have a candidate, you just use neutron to probe it, and you just ask what is the inelastic neutron scattering results, and you see you can have this kind of low energy linear dispersion, then it will be a signature that it is a U1 quantum spin liquid. Okay, so that's for this special case. But you can ask the question like, how about other spin liquid? Are there some generic feature that you can probe it? The unfortunate thing is that the answer is no, because it depends on what kind of entanglement structure. It will give you different kind of signature. For example, the toric model we discussed before, that model is notoriously difficult to detect because it is there's no response for anything. So, so at this moment, I only know numerical evidence. For example, you do the numerical study of this wave function, and you study the entanglement entropy, because numerical-wise, you can directly get your wave function. Then you have a lot of access to the to your ground state wave function. But there are still some very exciting results recently. Maybe I'll just go to there. This is just something. I'll just share with everybody. This is just a very interesting result that showed up yesterday from the Harvard group. They successfully used the artificial system, what's called the Rydberg atom, and they claim that they are able to see this kind of quantum spin liquid physics. But unfortunately, I read the article on the high-speed railway, so I don't have the access to the full paper. So if you are interested in, you can try to read the paper and see, how this kind of exotic phase of matter can be realized in an artificial system, such as the Rydberg atoms. So, so I just highlight some of the important things. They detect a signature of toric type quantum spin liquid. I don't know how they do that, but hopefully I'll read the paper soon. And they use optical tweezers to basically hold these ripple atoms and try to couple them in a very special way such that they can realize this phase of matter. That's my rough understanding. And also, there are some very exciting or amazing numbers of these qubits. It's like 219. I think that breaks the current record of any quantum computer, but somehow they are big groups, so there might be a chance that they are able to do that. And so basically, the message I want to say is that realizing these exotic phases of matter is not just a business that is within solid states anymore. Now people are trying to use very artificial way to generate this wave function and see whether they can use the really advanced quantum technology such as this quantum computer to really understand these phases of matter. Yeah. Okay, so I think that's a little bit jump ahead, but I think that's fine. Thanks for the question. And are there any other questions? Yes? Okay, so I think it is a good time to stop here. So I think that's a good idea. So I still have a bunch of things to talk about, but I think I already conveyed the idea that it is a very interesting research subject. If you are younger generation, you are looking for research topic, please try to contact maybe like Professor Liezhen Zhang, who is working in spin ice, or I think Tyrone also work on topological phases of matter like T-ice, and I think Jinghao is also working on something related to disorder, but I don't have time to cover everything. But that's the bottom line is like the study of quantum phases is really a very active research field. Like new ideas come in and new developments is made every day. So please contact them. Yeah, and thanks for the opportunity for me to share my result.
好，我们谢谢 Thank Professor Huang. Any question？ 任何问题，用中文也可以，我们可以帮你翻译。
不用翻译啊，其实可以直接讲中文，只是很不幸我没有准备中文的演讲。
有问题吗？学生、同学？其实我有个问题，因为那个你可以到那个，就是你刚才说那个实验的证据要看这个。
是什么类型的 spin liquid？
对，因为你说你刚才有一个建议说，你觉得现在没有看到是因为温度不够低吗？
针对
你觉得温度要多低才看得到？
针对 U1 spin liquid 这个 range 可能要到20 mK 以下。
可是现在 neutron 最低只能到50 mK，
所以说我说还没有
就差那30就看不到。
因为这个 bandwidth 很小啦。那当然应该说。OK， 所以这都是理论上你要做 estimation。那你做 estimation 的时候，重要就是你怎么放你的参数嘛。我们都知道放不一样的参数，你的 estimation 会变不一样。那这个是 based on 就是我们有一个大概了解，在 rare earth 里面，它的交互作用强度大概是1 Kelvin， 就是 dominate 那一个大概是1 Kelvin。那这个理论的 quantum fluctuation 大概需要在1/10的这个1 Kelvin 左右去做 second order perturbation。 所以这样子做下来，你就知道你的 temperature range 至少是0.01 K 左右。那个0.01 K 会给你就是这个东西的高度。所以你如果真的只到50 K， 你如果 lucky， 你可能可以看到它的一个点，但是你没有办法有那个 resolution 去看到它会直直的一条线这样子。只有这样的效应会产生这样的结果，还是有可能有其他效应会有？这是一个非常好的问题，就是我刚刚只有讲到 linear dispersion 嘛，对不对？ 其中一个可能给你 linear dispersion 的东西就是 phonon 嘛，对，其实有很多东西啊，但是第一件事情，这个系统没有 order， 所以说你不可能是 spin wave，OK？、那另外一个重要的现象是你看到它的 weighting 是越来越弱的，就是通常你如果是就是 linear dispersion， 你这里可能是就是 weighting 都一样强，但是这个东西有一个 signature 是它会慢慢的变弱。
这样的变化有可能看在实验测量的时候的一些行为会有关系。实际看到慢慢的变弱，有可能是因为
没错，你有可能会有很多其他理由，比方说你的 cross section 在 low temperature 变低了，就是这你没办法 rule out 掉。但是有另外一个东西是你可以去比较它的那个叫什么 slope， 就是 slope 其实对应到是这个 excitation 的 velocity 嘛。那 excitation 的 velocity 其实就和什么样的交互作用导致你会有这个 excitation 有关，所以你就可以去问说，这个 slope 是不是 落在你想要的 spin-spin interaction 的那个区间。如果今天你是，比方说 phonon， 那个就那个 energy scale 就会跟这个差非常多。那这是其中一个，但是我只能说，针对这个 material， 这个应该是最容易量到的。你可以量到，你可以问说我能不能 construct 更多其他的量，那你当然也可以量，但是就不太容易 identify 它这样。因为比方说，你说有 linear dispersive mode， 你为什么要用 neutron？ 你也可以做 heat capacity。heat capacity 也给你一个 special 的 power law， 但是缺点是，就像我刚刚讲的，第一件事你要做很低温的 heat capacity， 那个很难弄。然后第二件事情是 heat capacity， 如果在那么低的温度下，你可能只能看到一个 decade， 一个 decade 你要说它有某一种 special power law， 其实没有人会相信。所以 neutron 可能在这个 case 还是比较好的。但是有另外一个情况我没有讲，我没有机会讲另外一个 family of spin liquid， 这个 ruthenium chloride。最近他们很红的原因是因为你可以去量这个 ruthenium chloride 的 thermal transport。那正常的 particle 你丢一个，你知道就是在 edge 上如果有 channel， 它会被 quantize as 就是一个那个叫什么 whole viscosity 的 unit，OK， 你就是整数倍的。可是这个材料如果它实现 quantum spin liquid 的话，它会有一个奇怪的行为是，你在 edge 上的 thermal transport 会是那个量的一半，就是 half quantized 的。那这个 half quantized 的行为又很神奇的，有人有办法把它量到，就是这篇 Nature 2018年的 Nature。那当然就给大家很大的想象空间，你怎么会有一个东西刚好 quantize 在某一个 universal quantity 的一半？就是到底发生了什么事？但是你会遇到一个问题，就是也不是你会遇到一个问题，是实际上我们的 community 遇到一个问题是，这个实验的 reproducibility 很低。基本上目前好像只有日本的 group 有办法量到吧，在 Dresden 我记得很多 group 想要量都没有量到 ，OK， 这是第一件事。但是第二件事情是最近也有很酷的东西出现，是2021就今年的文章。除了这个 exotic 的 have quantized value of thermal transport， 这个材料还发现一个很奇怪的事情是，它是一个 insulator， 但是你去量它的 quantum oscillation， 它会有 signal。就是它会看起来好像它有 Fermi surface， 但是它却是一个 insulator， 所以就出现一个问号，就是我怎么样去把这个实验数据有办法有效率的解释它？理论上他们应该是真正的 insulator， 这个东西是 Ang 做的，在 Princeton Ang 他应该不会搞错这东西到底是 insulator 还是它不是，对。哦，对，我知道，就是如果你是在 theoretical wise 的话，你会有这个问题，但他们是我不知道这是什么鬼东西，我就直接量的，就是插下去，然后量它超过那个 threshold of defining insulator， 我就说它是 insulator 的那一种，它不是 theoretical 去 propose 的，所以他们实验上看到 quantum oscillator， 这是最让大家觉得吃惊的事情，因为 insulator 基本上你不会期待它有 fermion 嘛。这不会有 Fermi surface， 但somehow 他们量到了，所以这个现在还在问号中。可是就像我讲的，它有很强的sample dependence 的 issue， 所以其实你不确定是不是有什么东西 went wrong， 这可能还需要一些时间和其他的实验来研究这样。对，那对，大概是这样。
好，那如果没有什么问题，我们这个演讲课到现在为止。好，我们谢谢黄教授。
好，感谢大家。希望我没有 overtime 太多。你有帮我计时，真的太好了，我不知道，我一直讲下去。对吧？哎，
你那个谱是不是
哪一个？
你说没有 speed citation， 可是会有 fractional speed citation 啊，还是量得到？
你说哪一个？
就是你说到就是你说如果没有 order， 应该量不到 excitation。你说那个 excitation 应该是 magnum excitation。
没有，它不能是 magnum， 因为
它应该是要 spinor， 就是要 fractionalize。
这里的话，它是 fractionized 的 particle 没错，但是问题是fractionized 的 particle 在这个系统是 magnetic monopole 和 charge， 这个有古典的对应性，但是那个能量尺度会在这个的上面，所以说这个为什么特别的原因是因为你要量到 quasi particle 是可能的，就你有 gap excitation 在上面。 可是这个东西它是 gapless， 就是它是在底下的。所以如果今天你没有这个东西，我可以说我的系统有 particle-like 的 excitation。那 particle-like excitation 不需要 entanglement 啊，它就是可以是各种东西，我 make 弄什么鬼的都可以。但是它这个是比较奇怪，是它是 gapless 的。所以说你就有点像没有，就你可以说 OK， 这是一个理论，如果它真的量到，但是有没有其他可能？你会发现你很难 cook up 其他的可能性，除了一种可能就是你只能说它是 phonon 啦，因为 phonon 有一大堆这种 gapless 的东西，但是 phonon 一般来说不会有这种强度的 dependence， 这是第一件事，而且在很低温。然后第二件事情是，这个东西的 phonon 你要 benchmark 太简单了，你就找一个材料，然后没有磁性的，我把它换成没有 phonon 的、没有磁性的，我直接量 phonon， 我还是会量到一个 dispersion 嘛。那这个和这个应该要87%像，所以说你应该可以 tell 它到底是不是 phonon， 对吧？对吧？所以还是有方法可以做的，但是。是啊，而且这个还比马加拉还冷门呢。就是，哎，
先问。
哎，你好。
让学生问一下。
哦，老师谢谢。老师，我只想问一个基础，你刚刚那个演讲过程中提到这个E1 symmetry 的 emergent。
对。
那这个可以再讲，你说如果有时间可以讲比较细节一点，我想说。
哦，可以啊。
对。
可是。
多 elaborate， 它。
我看一下我有没有那个 slide。
我刚刚 get 到，好像你说在这个 spin liquid 里面。
我有这个 slide。
这个 divergence E等于0这个，所以它是在 dynamic 的状态下可能会出现像是那个 EM wave 这种。
等一下哦，我把这个打开来，然后打开。好，这个就是你怎么弄出那个 emergent symmetry 的方式，就是你有 two in two out 的 manifold 是这个东西给你的嘛？那你的 quantum fluctuation 是这个东西，那这个 two in two out manifold 是一个很多 degenerate 的 manifold，所以你从量子力学你会学到你可以做 degenerate perturbation theory，然后就开始做，然后你会发现你要得到最低阶的修正 degenerate perturbation theory， 你要做到第三阶。第三阶你会得到一个这个样子的东西，那这个样子的东西是什么？其实它就是一个flip of your spin， 就是如果你有一个 spin 的方向原本是绿色这个顺时钟的，这一项会做的事情就是把它从顺时钟翻过来变成反时钟。所以说这个东西基本上你可以问说，好，那形成这样子以后，那我怎么看到它有 local symmetry？ 你如果去看这个 spin 的这个 update 就是它基本上是在这个六角形上面绕圈圈嘛。如果是顺时钟，它变成反时钟。那如果你把这个 S plus 你把它重新用另外一个有点像是 gauge degree of freedom 的东西去写 exponential IA， 但这个 A 现在变 angular variable， 那你会说这个写法到底是什么？这个看起来很奇怪，因为这是比较奇怪，因为这有点像是你把你的 spin 的 degrees of freedom 用一个东西叫 quantum rotor 去描述，就是一个在圆圈圈上旋转的量子粒子。
那个 A 算是在这个六角形的上面的那个 angle 吗？
好问题，这个 A 是在这个六角形上面的每一个点上面，有点像你放一个quantum rotor 在上面，所以你会有 A， 这里有一个 A， 这里有一个 A， 这里有一个 A， 这里有一个 A。然后你如果把 S plus 换成 exponential IA， 那 S minus 就会是 exponential 负 IA， 所以说你的这个 spin exchange 就会变成这里是加 A， 这里减 A， 这里加 A， 这里减 A， 这里加 A， 这里减 A， 所以说你会有加，就是相反的方向，一个加一个减，一个加一个减。那这个是如果这个是你的 Hamiltonian， 你就可以问说，那当我就是系统就是这个如果是这个是我的 Hamiltonian 的话，它会有什么样的对称性？你可以去问这件事。那你就会发现，如果今天你有你在这里找一个四面体，就是因为它是一大堆接在一起的四面体嘛，你找一个四面体。然后呢，这个四面体它上面也有 SZ 4个 SZ， 你会发现这4个 SZ 它会是你可以 local 的做这个，就是用这个 total 的 SZ 在这个四面体上做一个做一个 U1 的旋转，因为你在XY space 做旋转，你的 SZ component 不会改变嘛，所以说当你做这个旋转的时候，你会得到的效应就是你这里会增加一个旋转的角西塔 1， 然后这里就会减少一个旋转的角西塔 1。当你做这件事情的时候， 所以当你这样做的话，你会发现这个交互中一个刚好是一个加一个减，就是会被消掉。所以 effectively 你就变成说，你在这个红色的四面体上，你可以做一个 local 的 U1 旋转，然后这里你也可以做一个 local 的 U1 旋转。所以说你的 symmetry 从原本的 XXZ 是 global 的 U1 symmetry， 当你在这个特殊的 manifold 下面，它可以被 promote 成一个 local 的 U1 symmetry。所以这是这个 model 比较奇怪的地方，对吧？对啊，因为你如果把 particle 从 111看过去，它就是一层卡勾美，一层 triangle， 一层卡勾美，对。是啊，但是有一个差别是，卡勾美的 loop 只有一个维度 ，particle 像这一种的，你可以这样接过来，然后它可以再接到一个很奇怪的角度，是六角形是翻过来的或干嘛的。但是其实这个不是主要的 difficulty 啊，就主要的 difference 是，你在2维和3维会有一个效应叫什么 instanton effect， 就是你的 spin liquid 在2维，如果你要 stabilize， 你需要有 matter field， 就如果你写 gauge theory 写下来，你需要 matter field 它才 stabilize。但是3维的话，你可以不需要 matter field， 你都可以有这种 stabilized 的 pure gauge 的 fluctuation， 所以这个才有办法活下来。应该说3维的这个模型是某种程度上比较简单啦，2维的那个真的就是我刚刚有讲一个 example 这里嘛，这个实验很有趣。一开始的时候，他跟大家讲说这个东西是 gapless spin liquid， 因为那个时候理论说是 gapless spin liquid， 然后后来理论做数值模拟说是 gap 的，然后他又开始量，然后又量到有 gap 了，然后现在又变成说就是你就很尴尬，所以我到底该相信你同一个组的前一个实验还是后一个实验？就会变成说他们好像就是有点像是跟理论的预测刚好都有一点 correlated 的，你就会觉得说是不是这真的是我们期待看到的中立证据，还是说其实？对啊，就是你会发现 result 一直在劝，它是一个 time dependent 的 conclusion， 你就会觉得说意思应该是还没搞清楚。对啊，对啊，对啊，都会有这种怪怪的。就主要是 low temperature 的 impurity 啊，他们现在好像还没有很好的办法 characterize 它。
反而是下面那个227比较容易做出
227，这个好做，但是有一个缺点是 serum 的 valence 在227里面，正常的 valence 是没有 magnetic。所以说你要做奇怪的事情，把 serum 弄成有 magnetic。
对，就是你的 x 那个 side 要选。
不是选 x 的 side 而已。就 B side 你要选 recurrent 或 stunning 是没错，但是如果你直接长 recurrent 或 stunning， 它的 serum 其实是，嗨老师，我帮你 promote 一下你的研究，看有没有多一些人做 spin nice。老师你要找我，因为我现在只有2天会在清大，我大部分时间都在中研院。对，不过 anyway， 总之就是 serum 在正常的情况下长，它其实会是没有 valence 的，所以你需要走奇怪。
最近一个问题是 C0 side， 它是 fluoride。
所以它旁边有很多奇怪的，不是？
它的 net constant 跟这个完全几乎一样，所以2倍后你根本不能 tell。
对啊，对啊，所以
说
很难 tell
呢，它可能就造成你一些 pattern。现在的问题是这些 defect 是不是出来的 pattern 会跟 spinous 一样？
这个我也不知道，因为这个很新，
对吧？不是很新啊，就是我们刚好在玩这个，然后玩了老半天，发现这个 fluoride 跟一样，
不容易处理。
我要问你一个，
好。对，不好意思，这个先把演讲会还给你。
没关系，这个我来处理就好了。monopole mass，